Hello, welcome to the second webinar dedicated to the GeoKnowledge Hub. Following the introductory words from my colleagues Doug, Lubia, and Karine, I will illustrate you the path as knowledge provider that we have been following to enable the Brazil DataCube application to be open knowledge and its inclusion in the GeoKnowledge Hub. INPE has a long tradition on researches related to creation of land use and land cover maps, mainly in the Amazon and Cerrado biomes. These are some of the consolidated projects which are carried out by INPE, often in collaboration with other institutions. PRODES has carried out the inventory of our clear-cut deforestation in the natural vegetation that has occurred in the Brazilian legal Amazon since 1988. The DETER system generates deforestation alerts based on the analysis of daily images from the CIBER satellite series. And the Terra class identify what the deforested areas detected by PRODES become. So our team at INPE has been working on research and development of methodologies and technologies to support these activities. This picture summarizes the methodology behind our work in the Brazil DataCube project regarding the creation of land use and land cover maps dealing with Earth observation data and machine learning techniques. So, we start from the Earth observation data cubes. They are temporal composites created by a best pixel algorithm. We use land use and land cover samples obtained by specialists using high-resolution images. So, from the data cubes, we extract the time series for each pixel associated to the samples. These time series are then used to training a machine learning model. In this particular case of this application, we use a multi-layer perceptron neural network. Once the model is trained, it is possible to classify the entire region being mapped. The output of the classifier are the probabilities of a given pixel to belong to each of the samples classes. With this probability raster, we apply a spatial smoothing model that homogenizes the map areas using Bayesian inference from the information given by the neighborhood of each pixel. So, and finally, the land use map is obtained by taking the most likely class. Therefore, the knowledge we want to share is the methodology we are developing. So our presentation will focus on how the various components related to this research pipeline are turned into resources in the GeoKnowledge Hub. In the GeoKnowledge Hub, all the components of an Earth observation application are represented by a knowledge package. The knowledge package contains all the essential elements of the application necessary to its reproducibility or replicability. In the case of our application, it has a knowledge base centered on some recent papers published by the team. And in this slide, we highlight the components of the application, which were documented and structured in the GeoKnowledge Hub as a knowledge package. It's worth mentioning that we are not only reproducing a specific article, we created an application based on the methodology and technologies we have been developing. So, in addition to sharing the data and the code, we wrote also some documents to help users understand each of the resources. These are documents that complement the scientific publications behind the application. Therefore, we created a short document explaining how the user could access the data cubes in the Brazil Data Cube platform as used in the application, a document detailing the samples, their classes, the data structure used to organize them, another document that informs where are the maps that materialize the result of the application and the interpretation of the values of these data sets, another document on the organization of the R scripts. In the case of users who will use the Brazil Data Cube platform, we described how they can enter in a sandbox with a set of Jupyter notebooks ready to be used with all the computational environment and auxiliary data already prepared, an equivalent document for a version with the RStudio integrated development environment, a document indicating how the user could build his own compute environment and use the application's script, and finally, a document explaining the application in general terms, our step-by-step guide for the application. So I'm going to start with the publications that are the basis of this application. There is a central paper with the methodology and technologies we used, one with the methods we use to evaluate and identify spatial-temporal patterns in the samples, and another one that could serve as a source of inspiration to the use of different machine learning algorithms and some variations in the methodology. The study area is located in the Cerrado biome in Brazil, in the northeast of the country. In the resource that describes the data cubes used by the application, the user will have a guide on how to access the data cubes. It explains how they are generated, what are their spatial and temporal coverage. For example, we use data cubes from CBERS 4, Landsat 8, and Sentinel-2, based on a 16-day temporal composite. We indicate the portal where they can obtain this information and the address of the stack services that the user can use to access the data cubes. The training and validation samples are also explained in detail. The metadata and auxiliary documentation in the Knowledge Hub contains an in-depth description of the sample set used for training the multi-layer perceptron model used in the application. So we provide the data in many formats, in the CSV and the Esri shapefile formats as shown here. The training samples contain almost 1,000 data points organized in 3 classes, crop, natural vegetation, and pasture. They were collected by visual interpretation of high-resolution images. And in the same way, we have a resource with information about the sample set used to validate the classified maps. So this data is based on the project Cerrado. To make things easier for the user, we provide the samples in the format used by the software stack used by the application. So besides the Esri shapefile, there are RDS files that include the time series related to each sample and for each pair of satellite sensor. So we have the spectral temporal signature related to the samples. And this is what will be used to train the machine learning model. The code shared is based on a set of R scripts. We use an open source license for these scripts. To make it easier for the user, we created a version using the Jupyter Notebook technology with a fair computational narrative of the application. We also built a version using R Markdown with the same computational narrative for those that prefer the RStudio environment. And the main technology behind the creation of the maps, is an open source R package named SITS. We also described how the user can have a computational environment based on it. So the SITS package is designed to work with satellite image time series and to support most of the steps of the land use and land cover classification workflow, including sample evaluation, machine learning classification, and map post-processing. This package brings together a set of tools for time series analysis and visualization, such as self-organized map clustering and time series filtering. We have prepared some resources with a specific version of the SITS package and all the libraries needed to run the scripts or the Jupyter notebooks or the R Markdown. There are also instructions on how to use Docker images to prepare the environment on-premises hardware and how to access everything from the web. The last resource developed describes the set of thematic maps that are output of the application. As I mentioned in the beginning of the presentation, the classification output of the multi-layer perceptron model used in this application is a raster with one layer for each land use class. These layers contain the probabilities of each pixel belong to each of the classes. So we also shared the GeoTIFF files with these probabilities besides the thematic maps, and a document with an in-depth description of these files. The digital library of the GeoKnowledge Hub is the place for the users to discover the Brazil DataCube application package and all its essential related resources. So let's get into the prototype of the GeoKnowledge Hub digital library to see how we shared some of the components of our application. So a user looking for land use and land cover applications will find the package with the Brazil DataCube. So here is the knowledge package. From this package, we will have all the information of its components. Currently, the digital library does not yet deal with all the elements in an aggregated way, but it is already possible to locate the individual resources. So here in the main package of the application, we will find the metadata of authorship, the contact information, a description of the application, and the document that contains a step-by-step of the available components. So this document here explains in detail how the user can start working with it. So here we have the list of all the resources related to that application. In this lower part here, right now, we have only a list of linked resources, but in the future, we will have the components properly presented and ready for more detailed inspection, as we saw in the last presentation of the Knowledge Hub. If we go to a specific component, such as the samples, let's get the samples here. We will find the training and validation data sets in various formats. So here we have them in Esri shapefile format, the RDS, and the CSV. and also a guide that explains the structure and the fields of each of these files. We can, for instance, preview the CSV file here. And in the long run, we hope that users could, for instance, access a sandbox with everything prepared on it. So let's come back here to the resources and come to the software environment and select here the Jupyter Lab sandbox. So this sandbox here contains a detailed guide on how we have deployed the Jupyter Hub on our platform at INPE with a restricted access right now, but this could be one way to allow lowering the barriers for the reproducibility of this application. So if the user goes to this guide here, it will have the information to arrive into the sandbox. So as soon as the user sign in into the sandbox, it can start the computational environment based on our software with all the libraries already installed. And then the user can browse the material of the application here on the left panel here. So they will find all the Jupyter notebooks related to that application in a way that the user can work can learn with the annotations and with the code. So this is a cell code that produces this simple map here. And displays the samples that are going to be used for training the classification. So all the Jupyter notebooks will be available for the user in this environment since the extraction of the time series with information about the crop calendar, the sample data points, how they will extract the time series from a CBRAS data cube or a Landsat 8 or a Sentinel-2 data cube. Then for each data cube, there is a specific guide that covers the classification process again. So just to wrap up the presentation, INPE has a long tradition with open data and with free and open source software. This knowledge package is a start point for our team regarding the open science and reproducible research practices. So we are learning in the way also. We have many things that we can improve to share this application. The extra work realized in close collaboration with the GeoKnowledge Hub team also helped us to shape the communication of this application. We had many insights preparing this specific application in the GeoKnowledge Hub. The steps required to become a knowledge provider probably will be made easier as more people join the initiative and the practices are fine-tuned by more people. We still have a lot to learn in this road of reproducibility, but it opens the floor for more collaboration. The amount of investment in Earth observations applications calls for its reuse. And as my colleague Lubia said, decision makers need updated and trustable information. Science provides the methods and the technology to generate new knowledge. The scientific process can be very complex and dependent on different technologies and techniques. And the GeoKnowledge Hub is a bridge that provides the essential information for decision makers linked to all the aspects of the scientific practices. So in the name of the Brazil DataCube team, I would like to thank the GEO Secretariat for the invitation to participate in this second webinar of the GeoKnowledge Hub. Many thanks to all the Brazil DataCube team for their support on the preparation of this knowledge package. And finally, many thanks for your attention. Thank you.